homework as well. So this was the homework problem that Luke had assigned. And it's actually a modified problem from the 2016 AP Stats exam. It was free response number 2. When I say modified, it's the stem of the problem is exactly the same up here, but Luke did modify the sort of questions to make it a little bit faster and a little bit easier for you guys to read. And so I'm just going to give it a second here for my document camera to zoom in a little bit. Maybe I'll give you, 20 seconds or 30 seconds to read through the problem again. This is a heavier read here. There's no doubt about it. It's a little bit longer of a problem. So let me give you 20 or 30 seconds to see if you can just read it again. If you're brand new and didn't get a chance to look at the homework problem, this is what we assigned. So when I'm helping my kids get ready for the AP Stats exam, I like to say for every free response, if you have to spend a couple, 2, 3, 4, 5 minutes just reading through the problem, that's perfectly fine. It feels like when we grade these exams, both Luke and I are AP Stats graders, that sometimes kids sort of I dive into the problem maybe too quickly, and they perhaps don't even really understand what the problem's asking. So if you have to read it 2 or 3 times, that's perfectly fine. That's okay. The mathematics or the writing actually shouldn't take that long. So I'm just going to read it real quick. Product advertisers study the effects of television ads on children's choices for 2 new snacks. So the first sentence is there some relationship perhaps between television ads and what children choose for a snack? The advertisers use 2 30-second television ads in an experiment. So right now I'm thinking maybe it's experimental design, but I want to just keep reading and get an overall feel for the problem. One ad was for a new sugary snack called Cocoa Zooties, and the other ad was a new healthy snack called Apple Zooties. So I guess we have 2 different snacks that the students, the children could choose from, and then they watch some TV ad, and I still don't know exactly what they want me to do yet, so I'm just going to keep reading. For the experiment, 75 children were randomly assigned to 1 of 3 groups, A, B, and C. So if I jump down to my table here, I can see the 3 groups. I haven't added either across or down. And I'm a lefty here. I apologize for that. At times you're going to see my hand and you won't see what I'm doing, but I just added across, and if I add down, I get 19, 34, 56. And so I like to call this number over here my total. Some books call it table total. That's a Mr. Murphyism. So there's my 75, and it looks like they were evenly split up between my 3 groups, A, B, and C. Each child individually watched a 30-minute television program that was interrupted for 5 minutes of advertising. So we all complain about too many commercials, right? The advertising was the same for each group with the following exceptions. The advertising for group A included the Cocoa Zooties ad, but not the Apple Zooties ad. So for those 25 children who were in group A, the only commercial it looks like they saw was Cocoa Zooties. The advertising for group B included the Apple Zooties, but not the Cocoa Zooties. Boy, these are hard to read, aren't they? So B, it's the exact opposite. All these 25 kids saw ads just on Cocoa Zooties. The advertising for group C included neither Cocoa Zooties or Apple Zooties ad. So these 25 down here didn't see either one of those commercials. Looking at the numbers quickly, again, this isn't a statistical analysis, but it does appear that the children seem to like the Cocoa Zooties more than the Apple Zooties. regardless of which commercials they saw. But that's just my gut feeling, and I really need to do a statistical analysis before I can make any real decision here. So after the program, the children were offered a choice between the two snacks. The table below summarizes their choices. So A and B here, again, were not exactly what was on the AP Stats exam, but Luke modified that. So write the hypothesis. So my null hypothesis is going to be something like the proportion of students who chose each snack is the same no matter which ad they watched. So I guess it doesn't matter which ad they watched. So let me just step back a little bit. It's clearly chi-squared, and so we have the 3 chi-square testing. I'm going to hit this again on one of my PowerPoint slides, but chi-squared goodness of fit, that feels like I have some predetermined model and I'm comparing my data to that. This doesn't feel like it's chi-squared goodness of fit. So the next decision we need to make is this chi-squared test for homogeneity. Luke did that on Friday. I'm going to do chi-squared test for independence today. And so you need to make the decision, which one of these chi-squared tests is it? If you're struggling, and sometimes it's hard to figure that out, you can always just write chi-squared test. The nice thing is the assumptions, the formula, the mathematics, the mechanics is all the same. And so chi-squared test for homogeneity, it feels like we have 2 populations. I'm comparing one variable, and I want to see, is there any difference between that? So this does feel like chi-squared test for homogeneity to me. My alternate is in many ways the exact same statement, except I add the word not the same. So the proportion of students who chose each snack is not the same, no matter which ad they watched. So we basically just add the word not the same. For the sake of time in my lefty writing here, I won't rewrite the alternative, but it's basically the same thing as I wrote in my null. And now we think they're the same, and in the alternative, we think the proportions are not the same. And that's really what this test is designed to do. So the 3 conditions, again, I think I mentioned on Wednesday that chi-square is what we call a non-parametric test. They're actually pretty easy. I like to think of random, and I like to think of my expected values, and then what we call our 10% condition. That's it. Much easier sort of conditions, things that we need to worry about when we're doing chi-square testing as opposed to means or proportions. So random, I believe it did say up here that the students were selected randomly. Again, for the sake of time, I won't write it, but on your AP exam, you would say, students were selected randomly, blah, 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 as stated in the stem above. The expected value, we can go to our calculator and get those numbers. I'll show you that when I walk through an independence problem, but those are all greater than 5, and somewhere on your exam, many times kids actually just write those expected values right next to the observed somewhere. They're all greater than 5, and so we can just say, all expected values are greater than 5. And that's a good thing. If we have a really small expected value, it can artificially drive my chi-squared statistic higher, perhaps leading me to reject the null hypothesis when we perhaps shouldn't have. 10% condition, we want our population to be greater than 10 times our sample size. Other books, other teachers may say the opposite, but it's really the same thing. And so is our population greater than 10 times 75? Is our population greater than 750? And I'm going to call that an assumption. This feels like the random. I can check that. I can read the problem again. Expected values, I can mathematically check or confirm that. This here is an assumption. I really don't know how big the population is, but we're talking about children, and let's talk about the children in Bangor, Maine or something. And clearly, most populations of children will have more than 750 students. So I think we're good there. I think we've met the conditions. So again, that was the homework for the other night. Hopefully you had a chance to do that. If not, don't worry about it. And I'm back to my PowerPoint here. And this again was just the homework problem. So let's just keep moving forward. And so what do you really need to know when you're doing a chi-square test? Chi-square is just hypothesis tests. There's no confidence intervals. So sometimes my students will say, boy, Mr. Murphy, it feels like this is easier than either hypothesis testing with means or proportions because there's just hypothesis tests. Now, again, we have those three tests, right? Chi-squared goodness of fit, chi-squared test for homogeneity, and chi-square test for independence. This is the only formula we're ever going to use with chi-squared. Chi-squared is the sum of the observed minus the expected squared. So the numerator is always going to be positive divided by expected. This formula is given to you on the AP Stats exam, so no worries about it. And we talked about chi-square being a non-parametric test. So again, here are our three tests. Chi-square test for goodness of fit. We compare our data to I call it a predetermined model. Many times these models have percentages, and we need to remember to convert these percentages to counts. Think M&Ms or Smarties or something like that. I think Luke may have done that the other day. You know, M&Ms does publish the percentage of different colors you can get when you buy a bag of M&Ms. Chi-squared test for homogeneity. Again, Luke did that on Friday. We're comparing two different populations, one variable. So that's what happened in the Zudi's problem. Chi-squared test for independence, which I'll get into today. We have one population and we want to compare two or more variables. So that's, I guess, perhaps the harder decision sometimes for my students is a chi-squared test for homogeneity, Mr. Murphy, or is a chi-squared test for independence? We need to calculate degrees of freedom. So we'll talk about that. We need to check conditions. I guess we just did that again. There's just those three conditions. Data was randomly selected from the population. That's pretty much going to be in the stem of the problem, or where we may not even be able to run our test. All expected values, or at least 5, we'll mathematically check that later today. And then our 10% condition, our population is at least 10 times our sample size. So the conditions are easier. There's less things we have to check here. So a chi-squared table, once again, you'll have this on your AP Stats exam. And our calculators can perform all of these tests and get all of the mathematics for it. I do teach my children, my students, how to read a chi-squared table. Some teachers do, some don't. I'll leave that up to you and your teachers. You can see over here on the left-hand side, we do have degrees of freedom, and then we have upper tail probability here. So let's walk through some problems here. Again, chi-squared test for independence. The data comes from a single random sample from our population. So we have one population. We have two or more categorical variables that we are interested in seeing if they are related. You'll see the word related sometimes, associated, independent. All of those three words in many ways can mean the same thing. And those are perhaps clues. Our data is typically shown in a two-way table. Not always, and a two-way table doesn't necessarily mean it's chi-squared, but almost always you'll see it. Degrees of freedom, we have the number of rows minus 1 times the number of columns minus 1, or R minus 1 times C minus 1. We calculate expected values. We do that by row total times column total divided by the total. So you'll probably hear me later today say total. We can use our calculators to get these expected values. But it could be faster and easier to use the formula above. On a multiple choice question, I think it would just be easier to use this formula here to calculate an expected value for a certain cell. This formula is not given to you on the formula sheet, so that may be something that you just want to keep in the back of your mind. And of course, there's no chi-squared on this year's test anyway, but for future knowledge. So here's a multiple choice problem from the 1997 exam, multiple choice question 14. I give this to my student. I actually give this to my Algebra 1 or Algebra 2 students, and I use it really early in the year in AP Statistics, and it just gets kids thinking about, is there a relationship between these two variables? So I'll give you a minute or so to read through it. I'm not going to do the math here because the math is pretty easy, and we can perhaps answer this question without even doing a chi-squared test. So I'll give you a minute or so to read this problem, and then we'll talk about it. So in this two-way table, they actually gave us what we call marginal totals out here in the margins. If those numbers aren't given to me, I'm probably going to just, as a math teacher, put them in. So sometimes those are given to you, sometimes they're not. So a survey of 57 students was conducted to determine whether or not they held jobs outside of school. Okay, so it looks like I'm comparing your class, what class are you in your high school versus your job status. So I'm comparing two variables. I assume these students all came from one school. And so this feels like chi-square test for independence. I have one population, one school. I've hopefully randomly surveyed 57 students. And I want to see if there's some relationship between your year in high school, are you a junior or a senior, and or your job status. Two-way table above shows the number of students by employment status, job, no job, in class, junior or seniors. Which of the following best describes the relationship between employment status and class? I guess I'm not seeing the word random here. That I read it again. This was 1997, which was a long time ago. It was our first year running AP Stats. I think today you'd probably see the word random in there, but let's assume it was random. So without doing a whole lot of math, it looks like 13 out of 18 juniors have a job. Well, that feels like it's almost 70%. Yeah, 72% of the juniors have a job. And it looks like 13 out of 39 seniors have a job. Well, I can do that one in my head. That's pretty easy. That's 1/3, or 33%. So boy, it sort of does feel like the juniors have. Sorry about that. It does feel like the juniors have a much higher percentage of jobs than the seniors. So which of the following best describes the relationship between employment status and class? There appears to be no association. That doesn't feel good. There appears to be no association. It doesn't feel good. C, there appears to be an association since there are more seniors than juniors in the survey. I think I like the first half of that. I'm not sure I like the second half of that sentence. There appears to be an association since the proportion of juniors having jobs is much larger than the proportion of seniors having jobs. Yeah, the answer is D here. And again, I like to actually give this problem to my students long before we get to chi-squared, and sometimes long before they even get to AP Stats, just thinking about, working with two-way tables, seeing if there's some relationship between job status and your year in high school. Okay, so here's another multiple choice question. I think I introduced this really quickly on Wednesday when we first met for our first session. So this is the 2012 multiple choice question number 30. Again, we'll walk through this one really quickly. I do want to kind of walk through a free response question for independence and go through all of the different steps and whatnot. But maybe while I'm reading, just think about, does this feel like a chi-squared test? And if so, is it chi-squared test for goodness of fit, chi-squared test for homogeneity, or chi-squared test for independence? Just to see if you can figure out which one of the three tests it is. In order to plan for its next advertising campaign, the trendy motor vehicle company is investigating whether the type of vehicle and the color are related. Okay, well, there's a little clue right there. Is there some relationship between the vehicle color and the vehicle type? So I think I I think I know where this is going, but let's just keep reading and see if there are any more clues here. Each person in a random sample of size 275 selected from the company's mailing list was classified according to type, car or truck, and the color of the vehicle he or she drove. The data are in the table below. So does this feel like a chi-squared test for goodness of fit, chi-squared test for homogeneity, or chi-squared test for independence? And again, independence would be one population comparing two or more variables. And so it sort of feels like to me chi-squared test for independence, and the answer is E. And I guess I'm trying to again see, is there some relationship, some association between the color of the vehicle that people selected versus the make of the vehicle, car versus truck. Again, here's another multiple choice. I went through this the other day. Read it real quick. This is chi-square test for goodness of fit. So a geneticist hypothesizes that half of a given population will have brown eyes and the remaining half will be split evenly between blue and green eye. So there's that model I keep saying. There's some model that we're going to compare our data to. So the model is saying half the people will have brown eyes, 25% will have blue, 25% will have green. In a random sample of 60 people from this population, the individuals are distributed in the table above. What is the chi-squared test statistic for the goodness of this fit? So again, we won't run the test here, but this sort of feels like a classic goodness of fit test to me. I have a predetermined model, 50%, 25%, 25%. I've collected some data randomly and I want to see how good, how well does it fit my model? So that's kind of a classic goodness of fit problem. Okay, so we're going to look at a free response here, and I'm going to walk through I guess all of the four components of what we're typically looking for when we do a free response question. So this was from the 2003 AP Stats exam, and it was free response question number 5. So in a typical year, you would get 6 free responses. This is not a typical year. And right now, I'm not sure those decisions have even been finalized 100%, but this Friday, April 3rd, there's going to be more information released about this year's exam. So stay tuned. We do know it's 45 minutes long. And we do know that it's just free response questions. So I'll give you a minute to read it. And at some point, I'm going to switch over to my document camera. And I'm going to do the math out, and I'm going to show you how to use the calculator and pretty much all of those different things. So see if you can, when you're reading through the problem, see if you can figure out to yourself whether this feels like chi-squared goodness of fit, chi-squared test for homogeneity, or chi-squared test for independence. I just switched over to my document camera, and I'll give you another minute or so if you want to just finish reading that, and then we'll walk through it, and I'll show you all the different steps, including where to find things on your calculator and all that good stuff. Okay, we have a random sample of 200 students. Boy, that's good to know, right? Was selected from a large college in the United States. That's also another clue. Each selected student was asked to give his or her opinion about the following statement. The most important quality of a person who aspires to be president of the United States is knowledge of foreign affairs. So students were asked a quote, I guess, and they were asked their opinion about that. Each response was recorded in 1 of 5 categories: strongly agree, somewhat disagree, neither, somewhat agree, strongly agree. The gender of each selected student was noted. The data are summarized in the table below. So here's my classic two-way table. And I need to make a decision right now, which chi-square test do I think it's going to be? Let's see what they want me to do. Is there sufficient evidence to indicate that the response is dependent on gender? Provide statistical evidence to support your conclusion. So we're looking for a full-blown inference test here. We're going to need to walk through all the different steps, and so I'm going to do all that with you guys. But does this feel like chi-square test for independence? One population comparing two or more different variables. So I think it is, and I gave you a little clue here, right? I actually wrote out chi-square test for independence. So it feels like I'm comparing the response, what your opinion of was, or whether you agree with that quote or not, versus your gender, male versus female. Now, there are some clues here, dependent on gender. And so there are times when in the stem of the problem, there's some clues leading us to where we want to go. So the first thing I like to talk to my students about is writing down the name of the test. So this is a chi-square test for independence. The nice thing is if we do that, and in past rubrics, assuming it will happen in the future, is students can either write down the name of the test or the formula, but they don't need both. And so the formula for chi-squared isn't too bad, but again, naming the test feels like the first thing that I want to do. It feels pretty logical to me that that's the first thing. And so if you do that, then you do not need to write down the generic formula. I may do it just for the heck of it. I don't see any totals here, so I'm just going to try and do some quick math here. 30, 40, 40, 50, 40. And if I add those across, 70, 110. So I get 200 there. That's good. If I add across this, I get 25, 40, 65, 90. And if I females, 45, 70, 110. And so everything adds up, and that's a good thing. Would we want our males and females to be close? I think the answer is yes. I think the answer is yes. Again, the data was selected randomly, so what we get. If there were one male and 199 females, that might bother me more. But I don't think it's going to 90 and 110 feels okay, and so I mean we would want that to be about 50-50. But again, when we randomly select data, we get what we get, and we live with it. So the first thing I want to do is my null and alternative. So the null is that the response to the quote and gender are independent. There's no relationship between your response to the quote and your gender. Again, I'm a lefty. I apologize. My handwriting is atrocious. I've been working on it for years, but it doesn't seem to have gotten any better over the years. My alternative, in many ways, I just add the word not. So my response to the quote and gender are not independent. I guess that's it. Are not independent of each other. So I guess that's what we're really trying to figure out here. Is there some relationship, association between gender and your response to the quote? And that's why we're going to run the test, and we're going to run some numbers, and we'll talk about a good conclusion and all of those things. So that's sort of my first step, is I just do my null and alternative hypothesis. Of course, I do want to name the test right up here. That's critical, and that's really the first thing I want to do. My next step is I want to check conditions and assumptions. So what do we have? Just the three things, right, for chi-squared. So the 200 students were selected randomly, as stated in STEM or problem. Again, that has to be there pretty much in every problem, or we really can't even proceed with the problem. So it's always good to rewrite that though. Okay, my expected values might all have to be greater than 5. So I'm going to do one out mathematically, and then we're going to switch over to the calculator, and I'll show you how to do that on the calculator. I'm assuming Luke did that as well. So for this cell right here, male and strongly disagree, to get the expected value, I do what? The row total times the column total divided by what I like to call total. Books call it sometimes table total or something like that. Well, the row total, there were 90 males, and the column total was 30. So there's my column total, there's my row total, all over 200. So 90 times 30 divided by 200 is 13.5. So I would expect to get 13.5 males who strongly disagree with that quote. Now, this is an expected value, mean or average. So if you're saying to yourself, well, you can't get 13.5, Mr. Murphy, males. Yep, but it's an expected value or average. And so that's okay. And we do not want to round that. Okay, we do not want to round that. So I'm just going to get over to my calculator here. And I'm going to type in that data into my calculator. So let's start from scratch. I want to do second matrix. I'm not sure how much you've worked with matrices, probably algebra 2, right? Maybe you've seen some matrices in algebra 2. And I want to fill in matrix A, which is our observed values. So we had 2 rows and 5 columns. So it's a 2 by 5 matrix. And you hopefully have the numbers somewhere still. I'm just going to start typing in my numbers. And I'm just taking these right off the table. Probably much faster typing than I am. And so hopefully those numbers 10, 15, 15, 25, 25, those numbers line up. So all I've really done is type in the observed values into a matrix. What's pretty interesting, I'm not sure if Luke mentioned it to you, but when we do chi-squared, we actually run our test first to get our expected values. And my students always feel it's sort of backwards, which I sort of agree with actually. But so I'm going to go ahead and run a chi-square test. So stat test. I'm going to scroll down to chi-square. All of your calculators will have this, I believe. Some of the newer ones have chi-squared goodness of fit. If yours doesn't, don't worry about it. It's really not all that much more helpful. So if I go to chi-square test, hit enter, calculator is saying, did you, Mr. Murphy, type in your observed values in matrix A? I did. So when I actually run this test, it's going to actually put all of the expected values into matrix B. So I'm just going to run my test here. Again, I'm looking to see if my expected values are all greater than 5. I'm actually going to get my results before I get my expected values, but we'll come back to that. Okay, so I've run my chi-squared test. I have my chi-square statistic, but let's go back to the matrices. Second matrix. I want to go to matrix B. And here are all my chi-square expected values. And so I calculated one by hand. I don't want to do that just for timing's sake, but it would be the same process. And I'm going to write these on my paper. I'll show you that in just a second. So the nice thing is all of these values are greater than 5. So I'm going to go back. To my document camera here. And you see I've written in 13.5, 18, 18, 22.5, 18. I've physically written on my paper all of those expected values. As AP readers, we're looking for that. Students can't just say, you know, down here, all expected values greater than 5. You can't do that. We need to see some of these numbers. We actually want you to go to your calculator and get all those numbers, but you can't just say they're all greater than. We need to see some of the math somewhere. So what's our third condition? That the population wants to be greater than 10 times my sample size. My sample size was 200. So 10 times 200 is 2,000. Again, I would probably want a sentence like, it is reasonable to assume the population of students in a large college is greater than 2,000. I don't know that for a fact. There's no way we expect you to know that for a fact, but that's a reasonable assumption, right? So I have my 3 conditions, my randomness, my expected values, and my population, what we call the 10% check. So for our third step, you know, your teachers may have called it mechanics or math or something like that. If I've written down the name of the test somewhere, which is the first thing I want to do, I do not need to write the formula down. So I do not need to write the chi-squared formula and plug in a whole bunch of mathematics. I do not need to do that. So I think test taking strategy would not be to do that, and that will hold for means and proportions, which Luke and I are going to review next week. So if you write the name of the test, and that feels like it's the first thing I want to do on every free response question, then you do not need to write out the formula. So I'm going to go back to my calculator, which I've already done, right? When I was working to get those expected values, I had run my test. So let's just run it again. Stat, test, chi-square. I observed is in A. The calculator will automatically put those expected values in B. I want to calculate it. So my chi-squared statistic is 8.92. We don't really care about too many decimals. You want a few more decimals, that's fine. My p-value, my probability is 0.063, so that's important. And my degrees of freedom is 4. So let's go back to our problem here. I've written all those values down on my piece of paper here. So my chi-squared statistic, you need to show that, that's 8.92. My p-value, my probability, sometimes my students will write the probability or the probability value is 0.063. You know, we'll talk about that, but I'm typically comparing that to my assumed significance level alpha of 0.05. So that's going to help me make a decision here. My degrees of freedom is 4. And again, that's just row minus 1 times column minus 1. And so I've done my null and alternative. That's my first step here. I've listed my conditions and checked assumptions. I've listed my basically numbers right from the calculator, and that's really all we're looking for as readers. Okay, it's all we're looking for. Again, that's only if you've named the test. So I don't need to write the chi-squared formula. I don't need to plug in numbers. I don't need to do a whole lot of math. I can go right to the calculator. I can list those key statistics, those key values. So the last thing I need to do, I guess, step 4 is some conclusion. And that always needs to be in context. And I have somewhat of a generic conclusion here. I don't know if your teachers have something like that, but since our p-value, or our probability of 0.063 is greater than our assumed significance level, alpha is 0.05, we fail to reject the null. Now that's generic. I'm going to use that for every single problem, and it's somewhat boilerplate, but it does allow my kids to kind of say, okay, he does it the same way every time. And what we're really looking for is what we call linkage. We want you to link your p-value. Boy, I'm really messy, aren't I? Your p-value 0.063, it's your probability, is greater than your assumed significance level 0.05. Now, 0.05 is not the only significance level. That we read tests where some students put 0.01, some students point 0.07. What we're really looking for is you making a conclusion based upon your probability and your assumed significance level. If your probability is greater than your alpha level, 0.05, you fail to reject. So, but I do not have any context yet. There is not sufficient evidence. So the evidence wasn't strong enough here. There is not significant evidence to conclude that the response to the quote are dependent on gender. It doesn't appear that there's a relationship between gender and the response for the quote. So I've listed my p-value. I've compared that to my alpha level of 0.05. I either reject or fail to reject. We never accept. I don't like that word. That's sort of a bad word in statistics. Then I have a conclusion in context. There is not sufficient evidence to conclude that the response to the quote are dependent on gender. And in some ways, all I've done is restate the question. Is there sufficient evidence to indicate that response is dependent upon gender? And so if you're struggling with, context, just go back and read the problem again, and usually sort of embedded right in that problem is context for you. So that's walking through a full free response question and all the different steps, and that's a decent amount of work. So that could take you 5 or 10 minutes to go through, and that's okay. Again, the math many times is faster than fully understanding the problem. So if you have to read through it once or twice, that's perfectly fine. And you can write all over your AP exam and make notes to yourself. That's perfectly fine. So here's my 4 steps again. State my null and alternative and identify the parameter. Here I'm just saying it in words, so I don't really need to do that, but when we get to means and proportions, we will. We need to list assumptions and check conditions. Again, for chi-squared, it's just those 3 that we've talked about: randomness, expected value, and our 10% rule. Mechanics math, again, that's straight from the calculator if you've named the test. And then we always want conclusion and context. That's always do we want contextual analysis of whatever problem. This is pretty much just all the work that I just did for you. Here's another free response question, and I'm kind of keeping an eye on the clock here a little bit. Yeah, let me see if I can wind down here and then assign homework. Took me a little longer than I thought. Here's another free response question, 2017, so I guess a couple of years ago. The table and chart below summarize the age at diagnosis in years for a random sample of 207 men and women currently treated for schizophrenia. So two-way table sort of leads me to think that maybe it's chi-squared. Do the data provide convincing statistical evidence of an association between age group and gender in the diagnosis of schizophrenia? Well, there's another little clue. That feels like it's chi-squared test for independence. Some people call it chi-squared test for association. I'm looking to see, is there some relationship between gender and your age as it relates to the diagnosis for schizophrenia? So I won't walk through that for the sake of time. Here's another one, 1992, free response question number 2. I won't read through the whole problem, but it looks like we have two-way table. This is your skill of hiking. Are you a novice hiker or you're experienced? What happens when you get lost? Do you go uphill, downhill, or remain in the same space? So again, it feels like kind of a classic chi-square test for independence. Again, sort of when we read through the problem, do these data provide convincing evidence of an association? Well, there's a little clue right there. It's not a chi-square test for homogeneity. Okay, so at this point, hopefully you're feeling more comfortable with the 3 different chi-squared tests: chi-squared test goodness of fit, chi-squared test for homogeneity, chi-squared test for independence. We want you to be able to select the correct test and use it contextually. Similar to all of our other inference test procedures, you should be able to write a clear, concise solution in context. And that was sort of my 4th step there, where I compared my p-value, my significance level, and then made a conclusion in context. So here's the homework for tonight. Luke will finish it or start tomorrow with this. The following two-way table resulted from classifying each individual in a random sample of residents of a small city according to level of education, with categories earned at least a high school diploma and did not earn a high school diploma, and employment status: employed full-time, not employed full-time. So it appears that I'm comparing your employment status versus your education level. Feels like they all came from one population, one small city. So it sort of feels like a chi-square test for independence, but that's really not what we're looking for here. If the null hypothesis of no association between level of education and employment status is true, which of the following expressions give the expected number who earned at least a high school diploma and who are employed full-time? So I guess we're looking, we need to calculate an expected value for this cell and this cell and this cell and this cell. We could type all this data into our calculator. We could run the test. We could get the expected values from our calculator. Or if we remember the formula, row total times column total divided by total total, it might be easier to do. And that's really what your answer choices are here. So that's your homework for tonight.